Okay, this is a review of many problems from our worksheets having to do with permutations and combinations. Okay, so let's look at the first question. It says, in how many unique ways can the letters in the word math be arranged? When you are arranging letters, we are always talking about a permutation versus a combination. In a combination, order does not matter, but in a permutation, the order matters. So there are two things we need. We need to figure out what is n. N is the number of items we are choosing from. And then R is the number that you do choose. Okay, the number chosen or the number selected. So in this case, there's 4 different letters we're choosing from, and we're still going to select 4 of them. We're just rearranging them. So for a permutation, I'll write it up here, the formula N permute R. Sometimes they write it P with a bracket N R. Either way, the formula is the same. It's N factorial over N minus R factorial. So in this case, it's going to be 4 factorial over 4 minus 4 factorial, which is 4 factorial over 0 factorial, which, by the way, 0 factorial is always 1. So it's 4 times 3 times 2 times 1 divided by 1, and we end up getting 24 different unique ways to rearrange those letters. Okay, let's look at the next question. There's 12 executives, so that's going to be the number of items we are choosing from. So we can choose any of those 12, and we're trying to decide who's going to be president, vice president, and secretary. So it seems like we're choosing 3 of the 12, and order does matter. Why? Because if I choose 3 people, we can arrange them all differently, who's president, vice president, or secretary. So the order in which we choose them or the label that we put on them matters. So again, this is a permutation. So it's going to be 12 permute 3. Another way to write it is the permutation 12, 3. Either way, it's the same formula, 12 factorial over 12 minus 3 factorial. And in the end, when we calculate it all, there are 1,320 different ways to choose president, vice president, and secretary. Okay, let's look at this next one. We have 5 friends going to a concert, and we've got 5 seats in a row. How many different ways can they be seated? So again, the order matters, because if it's the same people but they're sitting in different seats, that's a different arrangement. So the order matters, which means we're talking about a permutation. We've got a total of 5 friends, and we're going to arrange them on 5 different seats. So we're choosing them all. So it's N permute R, which in this case 5 permute 5. You can also write it as permutation 5, 5. But how do we simplify that? That's 5 factorial over 5 minus 5 factorial, which is 5 times 4 times 3 times 2 times 1, divided by 5 minus 5 is 0 factorial, which is always just 1. And when we do all those calculations, we get there's 120 different ways for those 5 friends to sit at the concert. Okay, this next one's a little bit more complicated. They give us this word. We know it's a permutation. And we've got these letters. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 letters, but not so fast. They're telling us it's going to contain this string DEF. So DEF is in fact going to act like its own one item. So basically we have a choice of A, B, C. DEF has to stay together as a string, and then G, H, and I. So 1, 2, 3, 4, 5, 6, 7. So in fact, we're just choosing from 7 different choices of either the letter or the string of letters that we can rearrange, since DEF has to stay together. And we're putting them in 1, 2, 3, 4, 5, 6, 7 spaces. Okay, so it's going to be 7 permute 7, which is 7 factorial over 7 minus 7 factorial. Just to shortcut it, that ends up being 5,040 different ways to rearrange those letters as long as we keep DEF together. Okay, let's look at this next question. It says a pizza shop offers 10 different toppings and the customer's going to choose 3 toppings. So in this case, order does not matter, meaning it makes no difference if I put pepperoni followed by mushrooms or mushrooms followed by pepperoni. It doesn't matter what order. So in that case, it's a combination. And combination has a similar but different formula. We write n choose r, or you can write combination n comma r. And the formula is slightly different. It's n factorial over n minus r factorial, just like we did, but then we divide by another r factorial. So order does not matter. In this case, our n is 10 toppings we're choosing from. We're only going to choose 3 of them. So for this particular problem, we're saying, what is 10 choose 3? So that's 10 factorial divided by 10 minus 3 factorial and divided by another 3 factorial. When we plug that in our calculator, we get 120 different ways to choose 3 toppings out of 10 on your pizza. Okay, let's look at the next question. From a group of 15 artists, so that means n equals 15, we're choosing a committee. Now, a committee usually implies that order doesn't matter. Doesn't matter who you pick first, second, third, fourth. They're all going to be in the group together. So this, again, is a combination. We're choosing 4. So we're saying 15 choose 4. So that's 15 factorial divided by 15 minus 4 factorial, 4 factorial. We plug it in our calculator, and we get 1,365 different ways to choose a committee of 4 people from a group of 15. Okay, let's look at this next question. A deck of cards has 52 cards, so we're choosing from 52 cards. How many different 7-card hands? That means you're going to take 7 cards from the 52. So R equals 7. And how many ways can we do that? In this case, order does not matter because once you grab your cards, you can rearrange them in any order you want. It's still the same group of 7 cards. So if order does not matter, that's a combination. So we're going to say 52 choose 7, which is 52 factorial over 52 minus 7 factorial, 7 factorial. And when you put that in your calculator, you get, wow, it's a very big number. It looks to me like 133 million, 784,560. So many, 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 many ways to deal 7 cards from a 52 card deck. Okay, this next question's a little more complicated, so let's read it carefully. A student needs to select 2 electives from a list of 5 humanity courses. So that means we're starting with 5, and we're going to choose 2. Order doesn't matter, because what's the difference if you say you're choosing the first class and then the second class? Order doesn't matter which way you choose them. So we have 5 to choose from. We're choosing 2 of them. And then it says this word, and. And remember, and in math usually means times. And then it says, and 3 electives from a list of 7 science courses. So we've got 7, and we're going to choose 3 of those. So 5 choose 2 would be 5 factorial divided by 5 minus 2 factorial, 2 factorial. And then 7 choose 3 is going to be 7 factorial over 7 minus 3 factorial, 3 factorial. It's a lot to simplify. Let's see what it is. Well, it turns out 5 choose 2 is 10, and 7 choose 3 is 35, And so if we're going to do both of those things, we combine them by and we multiply, and we get there's 350 total ways to make those selections. Okay, these next questions talk about the binomial expansions, and they follow a very specific pattern. The first thing I want you to do is I want you to look at the power. That power of 3 means that there's going to be a total of 4 terms when we expand it, when we multiply it out. And again, the reason we're doing this is because if we did it the long way, p plus q times p plus q times p plus q, it would be very time consuming to do all the different multiplications that we have to do. And then after we did that, we'd have to do the same set of multiplications the third time. It takes a very long time. So instead, it follows a very nice pattern. So what we'll do first is we'll say there's 4 terms because it's to the power 3. And we look at the first term, p. P starts off to the power 3, p to the power 2, p to the power 1. And I'll write p to the power 0, but anything to the power 0 goes away. It's just 1. Now let's look at q. We'll have q to the power 0. We count upward by powers. Q to the power 1, q to the power 2, q to the power 3. And q to the power 0, we don't need. Anything to the power 0 is 1, so no need to write it. And one way you can check to make sure you haven't made a mistake is for each of these 4 terms, the 2 powers should add up to this original power. So again, this is just 3, which is 3. 2 plus 1 is 3. 1 plus 2 is 3. And then q to the 3, also 3. Now for the coefficient, we're going to do n choose 0. So n, so we'll do 3 choose 0, plus 3 choose 1, plus 3 choose 2, plus 3 choose, whoops, let's write it a little better, 3 choose 3. Now, by the way, more often I would have written it 3 choose 0, 3 choose 1, and so on. So you can do it that calculation, and when we calculate it, here's what we'll get. We get that 3 choose 0 is 1, p cubed. 3 choose 1 is 3, p squared q. No need to write q to the 1. Q looks a little nicer. 3 choose 2 is also 3, p to the 1, just we can write that as p, and then q squared. And then lastly, 3 choose 3. There's only one way to choose 3 items when you only have 3, and q cubed. So that's how you expand that binomial. All right, let's do the same pattern, but now it's a little bit bigger. So we've got to the power, something to the power 5. So that means there's going to be 1, 2, 3, 4, 5, 6 terms. And we will start with the a term. And we start with the highest power, a to the 5, a to the 4, a to the 3, a to the 2, a to the 1, a to the 0. This is going to go away because anything to the 0 power is 1. And then we will start with the b term now, and we'll say b to the 0, b to the 1, b squared, b cubed, b to the 4th, b to the 5th. And again, anything to the 0 power goes away. It's just 1. Now we will look at the coefficients. We start with this power 5. It's 5 choose 0, and 5 choose 1, and 5 choose 2, and 5 choose 3, 5 choose 4, and lastly 5 choose 5. So now 5 choose 0 is 1a to the 5th, 5 choose 1 is 5, a to the 4th b, 5 choose 2 is 10, a cubed, b squared, 5 choose 3 is also 10, but now it's a squared, b cubed, 5 choose 4 is 5, a b to the 4th, and 5 choose 5 is 1b to the 5th. So that's how we can use the combinations to get the coefficients of all of the terms of this expansion. Okay, this example gets a little more complicated, and you'll see why in a minute, but we start the same way. We say, okay, it's to the power 3, so we know there's going to be 1, 2, 3, 4 terms. Make these a little bigger. Okay, and we'll start with the first term. At this time, I'm putting brackets to the power 3, to the power 2, to the power 1, to the power 0, and what's inside the brackets is the 4x. 4x, 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 but again, anything to the power 0 is going to disappear. So same with minus y, so it's going to be minus y to the 0, minus y to the 1, minus y squared, and minus y cubed. And for our coefficients, again, we start with this power. It's 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Again, this way of writing it is exactly the same as writing 3 choose 0, 3 choose 1. It means the same. Okay, so let's start off by simplifying piece by piece. Let's do 3 choose 1 is just 1. I'm sorry, 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is also 3, and 3 choose 3 is 1. Okay, let's move on to the x terms. This is going to be 4 cubed, x cubed. This cube applies to both terms. Okay, y to the 0 goes away. Let me actually stick with all the x's. This is going to be 4 squared, and then x squared, and I'll do the y's at the end. Let's do this. This is 4 to the 1, x to the 1, and that one goes away. Now we'll move to the y's. Here we've got, remember, this is minus 1 to the 1, y to the 1. This is minus 1 squared, y squared. And this is minus 1 cubed, y cubed. So now the task is, let's simplify. 1 times 4 cubed is 64x cubed plus 3 times 4 squared times minus 1 to the 1. And in fact, it's, instead of plus, it's minus 48, and now it's x squared y. Okay, we'll move on. We've got 3 times 4 to the 1 times minus 1 squared. Make sure in your calculator you put that minus 1 in brackets. And we end up getting plus 12. And what's left over is x y squared. And then lastly, put this in brackets when you're calculating. 1 times minus 1 cubed ends up being minus 1 y cubed. And so that is our whole binomial expanded. Okay, now when you have a very big power, often the question is not going to ask you to expand the whole thing, because that would be 11 terms. It would be a lot. They'll just ask you about one of the terms, the coefficient of one of the terms in the expansion. So here's how you do this question. You first look at the power, and we're going to label that as n. And then you look at the power of the term, the b term, in the term that they're asking about, and we're going to call that j. So in this case, j equals 3. And it turns out that any j term, like that, you can get by this formula. So you can say the j term is going to be this formula. N choose j, the x term to the n minus j, and then the y term to the j power. So let's fill in those things for this specific problem. We've got n is 10, so 10 choose 3, and we've got x, which in this case our x is a. So we're going to say a to the 10 minus 3, and our y value is b, b to the j, which in this case we said was 3. So 10 choose 3 is 120, and a to the 10 minus 3 is a to the 7, b to the 3. So this is the term they are talking about. They asked about this term, and then they said, well, what's the coefficient? That's the coefficient of that particular term. So let's do it again, but now it's just a little bit uglier. So again, this power is what we call n. N is 6 in this case. And which term do we want? We want the j equals 4 term. And so the j term is going to be n choose j, x to the n minus j, y to the j. Now we'll plug in everything. So we've got 6 choose 4. Now instead of x, we've got 3x. So be careful here. 3x to the 6 minus 4. And then what's our y term? Minus 5y to the j, which is 4. Okay, so piece by piece, 6 choose 4 is 15. And then we've got 3x squared and minus 5y to the 4th. Okay, we've still got to simplify some more because this squared has to distribute and this power 4 has to distribute. So it's going to be 15 times 3 squared x squared times minus 5 to the 4 y to the 4. Okay, so we'll simplify some more. 15 times 9 times x squared times minus 5 to the 4 is 625 times y to the 4. So lastly, we'll multiply all these together, and we get a very big number, 84,375 x squared y to the 4th. And if you remember, the question itself was, what's the coefficient of the x squared y to the 4th term? That is the coefficient. Okay, now we're going to get into some more complicated problems. These are from week 11, and I'm going to do all of them while referencing the formula sheet that you'll have so you know how to think through things. So first of all, it says 3-letter codes formed using the letters A, B, C, D if repetition of letters is allowed. So a couple things. It's a code, which means that the order matters, and if order matters, that means it's a permutation. Okay, so order matters, it's a permutation, and let's look at the formula sheet. One other thing is that repetition is allowed. So we've already in those previous slides done permutations, combinations, but now it's a permutation and repetition is allowed. So we're going to use this formula, NPR, but in this case it just is n to the power r. So remember, n is always the number of things you could choose. So in this case our n is, we have 5 different choices, but we're going to have to put them into 3 spaces. It's a 3-letter code like that. So that's going to be our r. And so it's going to be 5 to the power 3, which is 125 different ways to choose it. Okay, so we've got a donut shop with 6 different types of donuts. So looks like there's n is 6. 6 is how many that we can choose, and we're going to buy a dozen. So we're actually going to select 12 of them. And how many different combinations, they gave us a hint there. It's going to be a combination. And repetition is allowed. So whenever repetition is allowed, it's a little bit more complicated formula because we could choose all of the same donut or mix it up. There's many, many more choices. So let's pull up the formula sheet and see what to do. Okay, we've got a combination with repetition. You'll notice 2 formulas. Either will work. I usually use this first one. And it says we're going to do, it's the combination of n plus r minus 1 comma r. So in this case, it's going to be 6 plus 12 minus 1, and comma 12. So that is 17, choose, not equal sign, no equal sign there. 17, choose 12. Another way to write it is 17, choose 12. And we get a final answer of 6,188 different ways to put 12 donuts in a box when we're choosing from 6 different types. Okay, this question, a bakery sells 5 kinds of bread. So n, remember, is the number of different things I can choose, types of things I can choose. I want to buy 10 loaves of bread, so I'm going to choose 10. However, it says we must choose at least 2 loaves of sourdough and 1 loaf of multigrain. So actually, let's think about this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2 of these have to be sourdough and 1 has to be multigrain, which means actually I'm really only choosing 7 of them because the other 3 are already chosen. So in fact, I'm going to say, look, I'm only choosing 7. And repetition is allowed because I can choose all of the same type of bread if I want. And so when repetition is allowed, it's a much more complicated formula. Let's pull up the formula sheet. Okay, so it's a combination because order doesn't matter. I'm just putting the things in the bag. And we have repetition. So it's C n plus r minus 1, comma r. So in this case, it's going to be 5 plus 7 minus 1, comma 7, which is 12 minus 1, 11. Choose 7, which is 330. Okay, here's another question, a spelling question. And anytime it's reordering letters, you always know it's going to be a permutation because order does matter when you're reordering the letters. But in this case, we have some repetition, lots of repetition, in fact. So it's a permutation with repetition. But it's not just your basic permutation with repetition. It's a permutation with what we call indistinguishable objects, meaning these, like if we switched the S's, it still would look like the same word. Or if we switched these I's, it would look like the same word. So in fact, we have to use this formula. So again, n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So the way this formula works is we do 11 factorial, but then we're going to divide by all of these letters if they have repetition. So M, there's only 1. How many I's are there in this? There's 1, 2, 3, 4 I's. How many S's are there? There's 4 S's. And how many P's? There are 2 P's. So what we do is for all those things that repeat, we're going to divide them. 1 factorial, 4 factorial, 4 factorial, 2 factorial. And you can know you've done it properly because 1 plus 4 plus 4 plus 2 adds up to 11. So you've accounted for all of the letters. And when you do this division, you get a final answer of 34,650 different ways to rearrange those letters. Okay, so now we have these questions about putting objects in boxes or on shelves, and they talk about this phrase distinguishable or not distinguishable. Another way you can say that is labeled or not labeled. Okay, so when they say unique, 7 unique books, it means 7 different things, and we can tell the difference as though they're labeled. And then 3 distinguishable shelves, meaning it does matter which shelf you're putting things on. So the question is, how many ways can you arrange the books on the shelves if the order of the books does not matter? Order doesn't matter, that's a combination. So it's a combination of putting distinguishable items on distinguishable shelves. Okay, so I pulled up the formula sheet and I see distinguishable objects, distinguishable boxes, same as shelves. They're both distinguishable, meaning labeled. They're all different. So they're saying n is the number of items, so n equals 7. K is the number of boxes or shelves, so in this case k equals 3. And the formula just says that the number of ways to do that is k to the n. So in this case, 3 to the power 7, which is 2187. Okay, let's look at this question. It's a little bit different. How many ways are there to distribute 7 distinguishable books, meaning they're all labeled, they're different, among 3 distinguishable shelves? Okay, but this time they're giving us specifics about each shelf. Shelf 1 gets 2 books, shelf 2 gets 3 books, shelf 3 gets 2 books. So they're telling us exactly how many go on each shelf. Let's pull up the formula sheet and see what it is. Okay, so we've got 2 different places where we talk about distinguishable objects, distinguishable boxes. This is the case here where, yes, it's distinguishable objects and distinguishable boxes, but they tell us exactly how many go in each box or on each shelf. So, okay, remember n is the number of items, so n equals 7. 3 is the number of boxes or shelves. Whoops, sorry, not 3. We call this k. K is 3. Okay, so what you're going to do is we say it's n factorial over all the different separations on each shelf. So in this case, we've got 3 shelves. We've got shelf number 1 is going to get 2 books. Shelf number 2 is going to get 3 books. And shelf number 3 is going to get 2 books. And remember, this plus this plus this should equal the total number of books. So we have the n factorial, and then we're going to have n1 factorial, n2 factorial, and 3 factorial. So in this particular case, we've got the 7 books, but on the first shelf, we have 2 of the books, so 2 factorial. Second shelf, 3 books, 3 factorial. Third shelf, 2 books, that's 2 factorial. And we get a final answer of 210 ways to distribute those 7 items on those 3 shelves, given these specific specifications they gave. Okay, we're going to do one more of these distributing items. So in this case, these are identical candies, so they're not distinguishable. They're not labeled. They're identical. Distinguishable. Okay, and we're distributing them among 4 children. So n equals 15. K equals 4. The children are like boxes or shelves. Let's pull up the formula sheet. And here is the formula where we've got indistinguishable objects going to distinguishable boxes. In this case, that's instead of boxes, it's children. And the formula is combination k plus n minus 1 comma n. So in this case, it's going to be 4 plus 15 minus 1 comma 15, which is the combination of 18 comma 15, which is 18 choose 15. So our final answer will be 816 different ways to distribute those candies among 4 children. Okay, that's all the practice exercises on the 2 worksheets from week 10 and week 11. Good luck, everyone.